Recorded's rolling. It is Thursday, September 11th. Yesterday, you guys did a projectile lab. Some of you guys turned it in. If you didn't turn it in yesterday, then turn it today, and I will score that and get that in the grade book. Yeah, thank you. You guys remember you were blasting those bounce balls horizontally off the balcony. You measured the height of the balcony. You spotted where the ball landed. You're trying to figure out the blast speed, and I walked you guys through the solution at the end of class yesterday. And all of the videos on Google Classroom if you need to review how they saw it. Interim one actually ended yesterday, and all your teachers have until tomorrow to get grades in. So definitely be checking focus for all your classes. Make sure there's nothing that says NTI, be not turned in with B0. Make sure you have all your grades in. There's nothing missing. Every once in a while, I get a paper that doesn't have a name on it, and I can't figure out whose it is. I do have a few papers taped up here by my bin. So if you see a paper up there that I think might be yours, see your handwriting or something, can you turn something in? Okay. We got picture day coming up on Monday. So whatever you want to look like in your photograph in the yearbook, there you go. That's coming up Monday. I think it's through your English classes, how they normally do that. There's parent-teacher conferences coming up next Wednesday, but your parents have to prearrange meeting times if they want to do that. Projectile puzzles. All right, so a while back, about a week ago, I gave you guys these projectile puzzles. I solved a bunch of these with you guys in class. For everybody has a different version. Actually, my plan today is just to review by just solving more and more of these in preparation for the quiz tomorrow. Okay. I had some specific ones I wanted to do with my AP students, but with you guys, I might more focus on these or take any individual questions you guys have. Okay, so since you guys know there's a quiz tomorrow on linear motion and projectiles, that's what it's going to be. Right now, my plan is to just do more like projectile review because you kind of get linear motion for free because it's all the same equations. You guys know the only equations you're really going to need tomorrow are just like these right here, right? Maybe, or actually, there is one more thing. How about, guys, what if you, right, so can you guys know these three? Right. All right, so the one other thing you might need is to break a velocity vector into components. Okay. Suppose you have a cannon that blasts a cannonball. Okay. At some, let's say 100 meters per second. And let's say this angle is 37 degrees. Okay. So the first step would be to break this into components. You guys, what's this vertical component right here equal to? B initial in the y direction. Is that 100 meters per second times what? You guys remember this? Is that a right triangle, basically?
Yeah.
Yeah, sine of 37 degrees. But you guys have calculators on your desks. I picked 37 degrees because I'm setting up a special right triangle. Okay. This should come out to 60 meters per second. You guys getting 60 meters per second? Or pretty close. I'm rounding a little bit. Okay. And then this looks like right here, v in the x direction, the horizontal component of velocity. That'd be 100 meters per second times what? Cosine of 37 degrees, which come out to like 80 meters per second in this case. Okay. Okay. So I think that's really all the formulas you need for tomorrow. There's the three kinematic formulas, and if you know sine and cosine, so you can break vectors into components. Right? That's all the formulas you need, and then you just have to know how to apply these. So if something's going at a constant speed, or in the case of projectiles horizontally, which would also be constant speed horizontally, right, then all you need is distance equals speed times time. Right? If that's true for a non-accelerating situation. Right? But if you throw something straight into the air and it comes back down, or you blast a projectile and it's like falling down due to gravity, right, that would be accelerating situation. So anything in free fall, I bet this A would be about 10 meters per second squared for Earth gravity. Didn't that be true? So like that. Right. Okay. We got how far is a function of time. We got how fast is a function of time. And we got how fast is a function of distance. Boom, boom, boom. This is good. Right. Okay. So, yeah. So, like I said, my plan is just to start solving a bunch of questions, do some examples. Unless you guys have any specific questions. Does anybody have any specific questions for review? No? Okay. All right. So let's do this. I'll throw you guys a linear question, and then we'll do some projectiles and yeah, just do as much as we can today. So first question, and I forget what's on the quiz. I made the quiz over the weekend, so almost a week ago. But I know we've covered everything. Let's say somebody throws a ball straight in the air with some initial velocity. Here, I'll give you guys a number. Let's say they throw it at 30 meters per second. And I want to know how high does the ball go? And I'll call it H max, or maybe just H or H max. Okay. So what is H max? Let's say what's the maximum height? How high does the ball go? In case you could word the question, anything like that. So I'm giving you, he throws it straight up at 30 meters per second. Question is, how high does the ball go? Now that can definitely be solved, right? So how would you solve it? Gravity. Gotta know gravity. Okay? Guys, I'm only explicitly giving you one number here. But you know, to solve any of these, you really need to be able to identify how many. Right? Three numbers. Right? So yeah, that's a good call. Is guys, gravity field would be
9.8.
Yeah, 9.8 or 10 meters per second squared. Right. A lot of times I'll just round it to this one, right? And that would be down, of course, right? Because he is throwing it upward. Right? He's throwing it upward. Gravity's pulling downward. That is a difference in direction. I might have to possibly be careful about a negative sign, possibly somewhere. Right? Think about that. But you do need something else too to plug into equations. What else do you really know about this? Okay, so if I'm saying H max, we're going from this initial case to this final case. Initial to final. Right? Point A to point B. What do you know about point B up here at the top? Zero velocity. Aha. I can say final velocity equals 0 meters per second at the max height point, which is exactly where we're going to. Okay. So now we got three kinematic values. Okay. So the target question is something about displacement, right? Maximum height. And well, G, VF, and V naught. Okay. So with all that in mind, can I fit this on one screen? Not really. It's kind of tight fit. Okay. What do you guys think? First, second, or third?
Second.
Second? All right. Let's try the second one. See what happens. Let's say you pick the second one. Say final velocity equals initial velocity plus AT. Well, I know this goes to 0, so that's nice. 0 meters per second. Oh, I know it's throwing at 30 meters per second. Okay, no, if I call this positive, that looks like I just called up positive.
Yeah.
So wouldn't gravity be pulling in the negative direction? Minus 10 meters per second squared times t. Yeah, 10t over. So 10t equals 30. This is meters per second squared, meters per second. Divide both sides by 10. And the units. Time is 3 seconds. Okay, so it takes 3 seconds to reach the top. Okay, so we did discover something new. That's true. But it doesn't quite answer the question. Yeah.
Couldn't have just said that because it travels 10 meters each second. Depends on the degree.
Yeah, that's another way to think of it. Yeah, I thought about this intuitively, second by second. Is it true after 1 second, maybe it's here? After 2 seconds, maybe it's here. At 3 seconds, so yeah, every second it is losing 10 meters per second. So 30 meters per second, 10, 10, 10. Yeah, it would take 3 seconds to reach top. That's a good way to think of it too. Yeah. Right. Now, we did find something. It just didn't answer the question. How high does the ball go? But maybe this could open more possibilities. That could be a helpful step anyway. So let's go equation shopping again. All right, so we just exhausted the second equation, so that one's done. All right, so what do you guys feel doing? First or third?
First.
First? All right. Oh, and you know what? We just found the time. So actually, that could be really handy. Yeah, that's right. Let's try the first one. So I'll go, here I'll just, so H max, that takes the place of this general displacement, could be H, right? Equals the throwing speed times time minus 1/2 gt squared. So H max we're solving for. They threw it at 30 meter per second. Now it's going up for 3 seconds, and then minus 1/2 10 meter per second squared, 3 seconds being squared. Guys, what's 30 times 3? 90, so that'd be meters. And then 3 squared is 9 times 5 is 45. What's 90 minus 45? 45. So that years. Right. That's the answer. 45 meters. Was it 45 meters? No. All right. So that was a long winding path. Right. We found the time first, and then we flipped it. This one. Oh yeah. Right.
What happened to the divide by 1/2?
This right here.
Yeah.
Oh yeah, so this all consolidated to get 45 meters. Okay. Because 3 squared is 9, right?
Yeah.
9 times 10 is 90 divided by 2 is
Oh.
45. Okay, yeah.
Yeah.
But you know what? You know what? We could have actually solved this whole thing faster just by applying the third equation from the get-go. Okay. Let's watch this. V squared equals, so V final squared equals V initial squared plus 2AX. Well, can I say that's minus 2G H max? Okay. And that would be H max if this V final goes to 0. We just talked about that before. So this is 0, squared, whatever. Okay. All right, so we threw it at 30 meters per second. Gonna square that. Minus 2 times 10 meters per second squared, and then H max is all for. Okay. So guys, what's 30 squared? 900. Okay, then I can add this over. So you got 20H equals 900. And these have units, of course. Meters per second squared, meters squared per second squared. Okay. Then divide both sides by 20. What's 90 divided by 2? 45. Ah, it's the same thing we got the other method. Oh, yeah. You guys see same thing, same thing? Same. Oh, yeah. Right, so you guys see that? Right. Right. Yeah, so actually that was a pretty good review because we just used all three of these kinematic formulas in a linear context. Right. Different paths through the force, same answer. Okay, guys good? Right. Let's do some projectiles. So you guys know the main categories of projectiles are either you have a cannon on a cliff, blasting and balls horizontally, just like your lab yesterday, right? Pow, blasting horizontally, right? Or the other case is a cannon on a plane blasting some angle, but we'll save that for later. Okay. So let's go with the setup from yesterday. Let's have some V blast here, and this falls into a projectile, just like your lab yesterday. That lands somewhere down here. I could have a height of the cliff H. I could have some distance that lands away X, and this is all in some gravity field. All some gravity field. So as long as I know any, you guys see these 4 variables? Okay. As long as I know any 3 of these, I can solve for the 4th one. Actually, you guys tell me, what do you guys want to solve for? D, H, X, or G? What do you guys feel like? H? All right, let's solve for H. Okay, so I need numbers for all these other ones. Let's have this last big here. Magic ball goes 69 meters per second. Let's have the let's have it land 20 meters out. 20 meters out. Now let's have this gravity field be 80 meters per second squared. There you go. Magic ball. So we got these numbers. All right, so already we're on a strange planet. Because we're on a planet with what? A weak or a really strong gravity field.
8 times strong.
Yeah, 8 times stronger than Earth. Could be 8 times as heavy. It probably wouldn't live very long. So yeah, so really, really big, heavy planet. Really strong gravity field. Hey, maybe it makes sense because we blasted really fast, but it didn't even go that far. Right? So what is the height of this cliff? Where do you guys want to start on this? Either horizontal or vertical. Should we start with horizontal information or vertical information? Yes, I like horizontal. Let's start with horizontal. Actually, you have to start with horizontal because we know 2 horizontal pieces of information, which allows us to solve for what other variable I haven't even written yet. Time. Aha. You guys, for projectiles, what's the only horizontal equation?
Meter. So, yeah.
X equals VT. That's it. Okay. He said horizontally, like once his cannonball leaves the barrel of the cannon, does it accelerate horizontally anymore? No, it just goes constant speed all the way across. Constant speed across the field. Right? Constant speed across. Okay. So that means that there's no acceleration horizontally. Like now there is a gravity field, but that acts vertically, not horizontally. So all these A's just go to 0. So zero, zero. The bottom 2 equations aren't very helpful. They just say the speed doesn't change. Right? And this one shortens to x equals vt. Right? That's it. So we're doing how far across equals how fast across times t. I'm going to modify this by throwing a little subscript x. Right there, subscript x. Say something about how fast it's going across the field. We're solving for this t. So we got 20 meters it goes. It's going at 69 meters per second for some time. So can you guys solve for time? All right, let's see what we get here. All right, we got 0.2898. I'll just call it 0.29 seconds. Right. Takes 0.29 seconds.
How'd you get that?
20 divided by 16.
Yeah. Yeah.
Oh,
Is that this little algebra shuffle?
wait, what'd you?
Okay. All right. That right? Okay. All right. So we know this ball goes from here to here in well that many seconds, well, a fraction of a second. That's kind of on par with reaction time, isn't it? Yeah. Right. So let's switch over to vertical. Okay. Remember, the question is what's the height of the cliff? Right? There's only one set height of the cliff that works for all these other numbers. Okay. So how do you guys want to get the height of the cliff now?
3.
Tell you what, let's avoid the third one for this reason. Okay. Now you know gravity field that would go in for this A, so that's okay. Actually, you also know V naught. Guys, what is V naught in this context? 0. Yes, yes. Do you guys see why? Here, guys. This is a common misconception. Students miss this all the time. Right? But Kai got it. Guys, this V naught is not the blast speed of the ball.
Starting speed, right?
Right, it's the starting vertical speed. Guys, we're about to craft a strictly vertical equation. And this cannonball leaving the barrel initially is not moving up or down, which means that in the vertical, this would be 0, wouldn't it? The initial would be 0. Right. Right. But okay, so we have check. We have both of these. Right. Now we don't know the height of the cliff, that's the question, but you also don't know anything about the crash speed yet. So you guys see how you would run into a dead end? You have one equation with two unknowns. Right. So okay, so all right, let's pick something different. What else could solve the height of the cliff? How about this one right here? Yeah. And also I like this one because we just found the time. Doesn't time link the horizontal back to the vertical? Right. So we can definitely use this one. So that's it. So say instead of some generic X for displacement, I'll call it H. Can I just put an H right here for height of the cliff? Right. Sometimes they call it Y. Right. So the height of the cliff equals V naught YT, which is of course just 0 anyway. We just talked about that. Plus 1/2 GT squared.
How do we know that it's 0?
Okay, so the initial starting and then starting of it.
Yeah. Okay, because we're setting up a strictly vertical equation. We just dealt with the horizontal. Now, horizontally, it's moving 60 meters per second across the field all the time. Okay. But vertically, when this cannonball is leaving the barrel, it's not moving up or down during the first instant. Right? It's only going to the side. Okay. The same as if you just dropped the ball. Guys, if you just dropped a ball at the same time you blast a ball horizontally, would they have the exact same vertical motion and hit the ground at the same time?
Yes.
They would. They would have exactly the same vertical motion. So, yeah, so that can also be modeled. That could also solve the height of the cliff too. Right? You can do it too. Right? So, yeah, so v initial in the y direction has to be 0. Right? Now, if you ramp up this angle to some other angle, this would no longer be 0. It would be something else. Right? We might do one of those later. Okay. Okay, if we have time. Let's take this 0.29 seconds. Pop it in right there. And for G, I think it's 80 meters per second squared, and pop it in right there. Right, I see it's speed up. So let's go. The height of the cliff then would be 1/2. Got 80 meter per second squared gravity field for 0.29 seconds, and that's being squared. Let's put it all together. So 0.5, 80, 0.29 squared. All right. Are you guys getting a height of 3.36 meters? Height of the cliff is 3.36 meters. Okay. Oh, hey guys, that balcony out there yesterday was about how tall?
4, 4, 5.
4 or 5.
Okay, yeah, about 4 or 5, depending on how you measured it. Right. Yeah, you should get a little over 4 meters. So here, what I'm saying is this cliff on this super heavy type alien planet is actually not that different than that balcony out there. Right? Now you blast it really fast to the side, and it only goes not super far because there's this huge gravity field. Yeah. But what I'm trying to get at is these numbers look reasonable. I think this looks about right. I can believe this. Right. You guys good? All right. So you guys good with the cannon on the cliff? Yeah, I forget what I put on the quiz, but I could totally ask a cannon on the cliff. I'd be surprised that I didn't have a cannon on the cliff. All right, let's do a cannon on a plane.
It's like the example on our puzzles one where the
Huh?
it's like pointed like at an angle up. And it's
Yeah, let's do that. Let's do that. Right. Let's do an angled cannon on a plane, and we'll do an angled cannon on a cliff. I think we'll have enough class time for all that. Right. So let's do angled cannon on a plane. So we're gonna blast a giant like the Great Plains. Yeah, the Great Plains. Okay, we'll do V blast at some angle theta from the horizontal. Um, I'll give you gravity. Here, I'll go ahead and give you guys first gravity. Let's call it 10 meters per second squared downward. And give you some numbers here. Oh, yeah, okay.
Does it matter if it's on a cliff, or does that just make it
Yeah,
just a horizontal equation instead of a vertical?
a clip would change the outcome. Like I could ask here, what I could ask is how far downrange? Like what's this distance D?
Yeah.
Like how far downrange?
But if it was on a cliff, then you would also need that on the height too, right?
Yeah, because if there's a cliff here, right? If it's a really tall cliff, we call it a cliff. It's just going to keep sailing sort of to the right. It's going to go even further. Yeah, that would make a difference.
Also, we have where it's going up at an angle, but it's also on a cliff.
Yeah, we'll do that too. Yeah. So guys, your puzzle, there's 3 categories of puzzles. Right. So the left side of the paper on the front is cannons on cliff aimed horizontal, like this one we just did. The 3 scenarios on the right is the one we're in the middle of doing right now. And then on the back, you got the hybrid cannon on the cliff at an angle. Right, so here, let's come up with some numbers. So for V blast, let's go 2. Why not? This little toy cannon. 2.0 meters per second. Let's have this angle right here be 5 degrees. Oh, I'm getting silly numbers. That's okay. We'll run with it. 5 degrees. And okay, 5 degrees. Is that really, really shallow? Is that like almost horizontal? Do you guys think this is not going to go very far?
No.
Maybe a couple meters or something. All right, I'm guessing. All right, we'll find out. I mean, take this basic shape. So when you see this, what's the first step? What do you want to do with this blast velocity? Can we do some component vectors?
Yeah, find
The vector components?
What
Yeah.
did 5 say? Like,
5 degrees. Theta is 5 degrees. So it's going across, it's going up. No, the picture is not the scale, of course, because 5 degrees is really shallow angle. Okay. But could this be 2 meters per second times what?
first one.
Cosine of 5 degrees. Aha. And this V initial in the y direction, that could be 2 meters per second times sine of 5 degrees.
would it be cosine of 5?
Yeah, cosine of 5 down here and sine of 5 up here. Yeah. All right, let's see. So 2 cosine 5 is almost 2 anyway. Guys, 1.99 meters per second. Right. I mean, 5 degrees is such a shallow angle.
Can we just round?
I mean, almost. Right. I'll call it 1.99. Right. Which is almost 2. The full blast speed is 2. I should pick a different angle. Here, let's go with a different angle. That's too confusing. Right. All right, let's go. Well, that doesn't make any sense either. Pick a different angle. Let's go. Here, let's call it 50 degrees. 50 degrees. Okay. Let's change this to 50. 50 degrees. Okay. 50 degrees we're doing now. Which actually does look more like my picture anyway. Let's do 50 degrees. Right, that'd be 1.29. 1.29 meters per second across. And then goes up at, if I change this to sine, this would be 1.53 meters per second. Okay. You guys get so far? Got a 50-degree angle, which actually looks pretty close to my picture. All right. Now, how far it goes across this D? Wouldn't that just be how fast it's going across, which is this right here, 1.29 meters per second for however much time it's in the air? Isn't that sure? Right. But we don't know how much time it's in the air. How could you figure that out?
20 and then 10 and 0.
Um,
You just count it out.
2.0.
okay. Yeah, you could count it out if it's like nice numbers. Yeah, it's something to do with this gravity pulling down, right? Because the stronger the gravity field, the faster it's going to pull it down. There's no gravity applied into space. Never gets gravity. So there's several ways to do this. There's several ways. One method is you could let's do it this way. Let's break this in half. Guys, could you go from here to the peak and say that represents half of the time? Could you do that?
Reaches 0.
Yeah, right. It'd be 0 vertical velocity at this point, wouldn't it?
Then there's calculating them.
Yeah. All right, so let's do this way. Let's go V final in the y direction equals V initial in the y direction minus G times T. Okay, except here's where I made it a little tricky. Because the full hang time would be back to the ground, wouldn't it?
Yeah.
If the full hang time is back to the ground, how much time is it right to the peak?
Half
Half. So isn't this like
times two.
t over two? Right, t over two. Right. And yeah, right. So the last step would be to multiply back into two so we can get the full hang time. True. Okay, so this would go to 0 meters per second at the peak. At the peak. That's where I'm getting the zero in the y direction. Okay. Oh, guys, what do I plug in for the initial in the y direction? 1.53 meter per second. 1.53 meter per second. Okay. And then G, I'm calling 10 meters per second squared and down. So the fact that you're kind of blasting up, gravity's pulling down, is it true that it has to be negative somewhere in your mouth? T we're solving for over 2. Okay. All right. So I pick the second kinematic equation. So we're sort of blasting up-ish. Gravity's pulling down for some time. How much time? Well, that's what we're solving for. But I know at the peak it goes to 0 meters per second vertically. Now that's where that comes from. Okay. Okay. Can you guys finish off the algebra here? Let's see. Guys, what's 10 over 2?
5.
5, and can add that over. So I'll have like 5t equals 1.53.
How do you know that 2 is divided by 1?
Oh, okay. Guys, this t, the t represents the full hang time because I want it to travel all the way back to the ground. So could it take some time t to go from here to here? Okay. And if that's true, then if I break this problem in half and I only go to the peak, isn't that half of the whole total hang time?
Yeah.
So it's really t over 2, isn't it? This is t over 2? Right. Whatever that time is. Right. Right. So by plugging t over 2 here, that actually is helpful in a way because I can let the vertical component velocity go to 0, which would also represent the peak. Right. So here's
Would it not be -5 because it's minus?
No, because
Okay.
whenever you switch it over, you have to put the like this plus turns to negative.
Yeah.
And then positive.
right. It is negative here, and then algebraically I just added that over, or added to both sides. Yeah. So there's a negative in this line, but when I add it over, everything becomes positive here. Okay? Which also gives me a positive time, which is good because it's telling me it's going to land in the future of blasting it from the cannon. 1.53 over 5. Okay. So I'm getting 0.306 seconds. Is that what you guys get into? Think about a third of a second. Okay. So that's how much time it's in the air for, right?
Oh, they're the multiply
Okay.
by 2.
Here. Yeah, we took care of that already. Yeah.
Oh yeah.
Okay. Yeah, took care of that already. Okay. All right. So here, let me recap what we have so far. So cannon on a plane ramped that up at a 50-degree angle. That's what we got. Then you break the blast velocity into components. So here's a cosine component and a sine component. So now we have hard numbers on how fast is it going across the field and how fast is it initially going up. Now I take that initial upward velocity, almost like if you throw a ball straight up, I can figure out how much time it's going to be in the air for. I set this kinematic equation, which is really just the second equation right here, isn't it? Right. Now, here's how fast it was initially going up. Just pop that in right there. Which is the sine component. That's where that came from. I know gravity's pulling down 10 meters per second squared, say for some time. And if I let it go to the peak, I know at the peak it's going 0 meters per second vertically, right? But one more catch is that only represents half the total hang time. So I'm really solving for t over 2. T over 2 is what here. Okay? Okay. Then if I let all the algebra play out, it tells me the full hang time. And that's the full hang time right there. Okay, okay, so we're real close. We just got one step left. And the last step is, here, I'll go back to my original page. I can say this d equals v sub x times the full hang time. Isn't that true? Okay. You guys, what is this v sub x equal to?
Wait, what?
How fast is the ball traveling across the field?
Or
Yeah, change the angle. So let's call it 1.29 meter per second. Okay. For how much time?
0.30.
Yeah. 0.306 seconds. Right? So it's always going across the field at that speed for that much time. So 129 times 306. I'm getting 0.39 meters. Right? You guys getting that too? Right? Yeah. Again, if I only launched it at 2 meters per second, which isn't that fast, but like right. Yeah, a 50-degree angle. Yeah, it only goes not even half a meter stick. Yeah, that looks about right.
What if it's only doing the half? Isn't 0.306 half-life?
No, this is the full hang time, right? Because okay, guys, there's two ways to handle this. You could put T, just regular T here, and if you did that, this would work out to 1.53 and then divide by 10. This would only work out to 0.15 seconds, and then you could double it after the fact. You could say time two. Okay. Now I put in brackets. I recognized from the get-go that that's only half of the hang time, so it naturally came out to this anyway. Okay. Yeah. All right. All right. You guys ready for a cannon on a cliff at an angle? All right, let's do. Okay, so this is like one from the back of your page. So got like a hybrid situation going on. All right, so cliff. All right, cannon. Blast the ball. All right. B equals. You know what I'll do is I'll just call this 100 meters per second. I'll do that. Cliff of some height. It's gonna way over here. Some distance away. Oh, it's like oh, it's D, right? It makes sense. Oh, it's D. Alright. If you guys G equals 10 meter per second squared down. Alright, guys go with the setup. This good? Right. One more thing. I gotta tell you what is this angle. So let's do components. Okay. Let's say this theta. Here, I'll write it out here because that's too cramped. Theta equals. Let's go 36.9 degrees. Let's do that. Right. And some of you guys might know why I picked that number. Right. Right. So, guys, what's the first step whenever you have an angle involved? You have to find the component. Yeah, components. There you go, components. So I'll call this V sub x, and that's equal to what times what?
C times cosine.
Yeah, 100 meters per second times cosine of 36.9 degrees. Okay. And wouldn't this be the initial in the y direction is 100 meters per second times sine of 36.9 degrees? Right. Right. Hey guys, what do you guys get? Or you might not even need a calculator if you know what I'm choosing that angle for. Or maybe you do, and you plug that in your calculator. What are these components coming out to?
39.964.
Aha! 80 meters per second and 60 meters per second. Aha!
What are sine and cosine like? How do we divide or multiply it?
Huh?
Like how does I don't know. I never really understood sine and cosine.
Oh, sine, cosine? Yeah. Okay. Okay, that's it. Right, so little side trip here. Okay. Do you learn a unit circle?
I know that's 360, but
Yeah. Okay. So if you start like at some angle on the x-axis, so let's say our starting place is the x-axis. Here's our start stop. I'll call this like 0 degrees, and I work up some angle theta, and I'm like going around the circle. Okay. And in this class, well, we're normally locked between like 0 and 90 degrees anyway. Sine tells you how high or low you are from this starting bar.
Okay.
Right. And cosine tells you how far right or left of the center line you are. Okay. So, guys, if I do sine of 0 degrees, isn't that like 0 height? Oh, look at that, sine of 0, 0. But guys, what's cosine of 0 degrees? Isn't that like this full distance right here?
Yeah.
So cosine of 0 is like 1, as in 100%. 100%. Right? Okay. How about what if I do 90 degrees? Guys, what is sine of 90 degrees? How high are you? 1 unit up. Or you put 1 full radius. So sine of 90 degrees is 1. But what's cosine of 90 degrees? 0, because you have 0 width from the center. Right? What about 30 degrees? Can that be pretty close to 30 degrees? Because what is sine of 30 degrees? Is that another way to say, like, how high are you right here? Is that about halfway up?
Yeah.
In fact, it's exactly halfway up. Hence 0.5. Right? But cosine of 30 degrees, isn't that like, is that most of the way to the right? So if I pop in a cosine, yeah, it's like 87% of the way. So this is like 87% of the way over. Yes, I do. Okay. So back to physics then.
Thank you.
Yeah, what we're trying to figure out is how fast is this ball going across the field? Like if you're up in a balloon and watch it going across, and how fast is it strictly going up? And of course, that's always changing because gravity's pulling it down. Okay. Right. So we got 60 meters per second across, or sorry, 60 meters per second strictly upward, which is always changing. The immediate starts slow. Right? And then 80 meters per second across. Now that stays the same all the way across the field. It's always going 80 meters per second across. Okay. And I picked 36.9 degrees because that would be consistent with a what triangle?
3, 4, 5.
3, 4, 5. You guys see the 3, 4, 5 geometry? 60, 80, 100. That's 3, 4, 5 by a factor of 20. Right? Okay. All right. So now, actually, you can't solve this yet because I never gave you a cliff height. Let's come up with a cliff height. How high is this cliff? Whoa, 54 meters. It's 54 meters now. The ball just decided. 54 meters. Okay. Got a 54-meter tall cliff. Okay, once I establish the cliff height, is there definitely some amount of time it takes to reach the valley below?
Yeah.
Yes, there is. So it's kinematic time. Now, if you're trying to find time based on cliff height, like a displacement, which equation do you think that's going to be? The first one. Yeah. All right. First one. Let's do it. So I would say the height. Well, here. Copy pasted. It's like x equals d naught t plus half at squared. That's straight out the poster. But we're going to modify it for the situation. Now, you guys tell me, do you want up or down to be defined as positive?
Yeah.
Down? Okay, down positive. So we're going to say down is positive. Right? And if that's true, doesn't this cannonball, where'd my cliff go?
Star is negative, right?
Yeah, it would be blasting vertically in the negative direction. That's true. But it ends up overall downwards from where it started. So that would be overall positive, wouldn't it?
Yeah.
Okay. So it's like this cliff height right here is 54 meters. Okay. So that's the H if you like. I'll say H equals. Okay. Okay. Yeah, this would be negative because you're blasting it upward. We're calling that in the negative direction. That'd be 60 meters per second. See, for some time plus 1/2. And then since gravity is pulling down, which we just called positive, I'll just add a positive 10 meters per second squared for some time being squared. Okay? Is that okay?
Wait, is A gravity?
Yes.
Oh.
Yeah. Gravity field is a type of acceleration, isn't it? Yeah. So in your projectiles, for the vertical equation, this is a vertical equation. I'll specify that. Vertical equation. Yeah, the gravity field is the acceleration. Yeah. All right. Yeah, we're trying to solve for t. I got a t squared, I got a t, I got a constant over here. We have to apply the what? Starts with the q.
Quadratic.
It's quadratic time! Quadratic! All right, guys, what's half of 10? 5? So I'll do 5t we're solving for squared plus this 60t. And then can I subtract over the 54? To get it equal to 0. Right. Now, that takes the form ax squared plus bx plus c equals 0. Get that? Right. These have units. Meter per second squared, meter per second, whatever. Which means I can apply the quadratic equation, which is hanging in front of me right here. If you're in class, you guys see it's right here. It says quadratic formula. Right. So t equals, see, negative b plus or minus the square root of b squared minus 4ac all over 2a.
Slow down.
Right. Okay. Now, careful with your negative footwork here, because you guys see two negatives?
Yeah.
Guys, what's negative, negative?
Positive.
Positive. Guys see that? Plus, plus. Used to be minus, minus, plus, plus.
So are you doing positive or negative with the 60? Or
Okay.
with the plus or
Oh, this plus minus? Okay. Guys, here, let's start with plus.
Minus 4 AC. Oh.
Yeah, okay. We'll start with the plus, which is the one we're going to use. Because it's like going forward in time, right? Going forward in time. Right. And I'll round back to, right. So negative 60, and then plus, notice I put this in parentheses. Guys, see if you can put this in your calculator. It's got square root of 60 squared plus 4 times 5 times 54. Close parenthesis closes the square root. Close another parenthesis closes the numerator. Then all divided by 2 times 5 is 10. I'm getting a time of 0.841 seconds. Okay. Now let me say 4. Is that right? Something's off. Maybe it's, hold on, let me try it again. 60 squared plus 4. Are you guys saying the same number I am? That doesn't look right. That does not look right. Let me reset this. I'm gonna try this again. Memory cleared. Something's off. You guys try it too.
How do we, is there a way to put, the plus or minus in the calculator?
No, you just have to do one or the other.
So,
So plus square root of 60 squared plus 4, 5, 54. Did do that right.
plus, so.
Huh. Maybe. Well, let's go with it. We'll just go with it. Something's off. I don't know.
Mine got an error.
Yeah.
That's
Be that right?
I got 5.841.
You got
Wait, negative it can be, oh, wait, no, wait,
what do you mean?
don't listen to me, sorry.
12 seconds.
How do you get it?
Shut up, that's
Hold on. Something's. I see what happened. I messed up. Guys, back here. Did you guys tell me that this should be negative? This should be negative. This
Yes.
is negative. Which makes this negative. Okay, now squares, whatever. This becomes plus. Okay, I'm so sorry, guys. Okay, I missed that negative sign, but I just fixed it. So get rid of this. Okay. This is, yeah. Okay. This is 12.84 seconds. Okay, so guys, that's a lesson on itself. If your numbers look squareball, if the numbers don't look right, then go back and check your work just like I did, because I missed that negative there, and that messed everything up. Okay. Now, if you plug in the minus version, you do get, say, or negative 0.84 seconds, okay, which doesn't make any sense, because that would get backwards in time, so we're not going to worry about that. So we're going to take this 12 seconds right here. Yeah, that looks a lot more believable. 12 seconds. Okay. Right, then, to finish this off, got just enough time to finish this off. I'll take that 12-second hang time and say, you know how fast the ball's going across the field, and you know how much time you can figure out how far it goes across. Isn't that it? Wouldn't that be the whole thing? Okay. So let's go x equals b sub x times t. And in place of x, I guess that's kind of like d, right? How far it goes across. This is going at 80 meters per second across the field. To be 80 meters per second for 12.84 seconds. 12.84 seconds. So 80 times 12.84. I'm looking at 1,027 meters. Yeah, that seems about right. Isn't that 1 kilometer?
Yeah.
1.0 something kilometers.
And we were trying to find T, right?
Yeah. Right, try to figure out how far. Yeah, 54-meter top cliff. That's like a skyscraper. 100 meters per second. That's really fast blast speed. You know, at some angle. Yeah, I could see that definitely going a kilometer. No, that's about right. It's about right. Boom, last step right there. All right, so that was about to ring. Close down this recording. If you have any last questions, let me know.